The simple harmonic motion model can be applied to many systems that undergo oscillations. One of those systems is a pendulum. A pendulum is a system where you have a restoring force, a force that always brings you back to an equilibrium point, and as a result, there is a back and forth motion, just like with a mass on a spring. We can see this even better if we consider the following applet. So here we have a pendulum and a mass on a spring. And to see that their motion is very similar, we can pull the pendulum and the mass back and then let them go. And you can see that as the pendulum swings back and forth, that's very similar to the motion of the mass on the spring. Both the spring and the pendulum draw their mass back to an equilibrium point. And there's also a back and forth exchange of kinetic energy and potential energy. So the potential energy is the biggest at the end points, because that's where the pendulum is at its highest point, so there's the greatest amount of gravitational potential energy. And at the endpoints is where the spring is stretched the most, so there is the most spring potential energy. Then at the equilibrium point, at either the bottom of the swing or when the spring is relaxed, the potential energy is there the smallest, and there is the most kinetic energy. So we can do an analysis of the pendulum motion and use its similarity to simple harmonic motion of a mass on the end of a spring in order to determine what the period of a pendulum is and some other interesting properties. So remember that simple harmonic motion always involves a restoring force. So that restoring force can be equated to some displacement from equilibrium. So next let's look more carefully at the pendulum. So if we look at the forces that act on the pendulum in the y direction, so we put down a coordinate system, and since this is going in a circle, we have some motion in a circle, we want to make sure that one of our coordinate directions points towards the center of the circle, because whenever you have circular motion, you want to analyze the forces towards the center of the circle, because the sum of those forces in that direction is going to be equal to the centripetal force, or the mass times the centripetal acceleration. So in this case, we can see that we have the tension force going towards the center of the circle, and we have a component of the gravitational force mg cosine theta, which is going away from the center of the circle. Those are equal to, when we sum them, the mass times the centripetal acceleration, since we have motion in a circle with a pendulum, and that's going to be equal to mass times speed squared over r, where the speed is the speed at this point in the motion. In the x direction, we only have one force, and it's acting in the negative x direction, and that is a component of the gravitational force. So it's this component here, and we've just drawn it, slid the vector and drawn it here instead, but that's going to be equal to mg times the sine of theta, since the x component is opposite this angle theta, which is also the angle of swing that the pendulum is currently at. So we can see that this force in the x direction is acting like a restoring force. It's bringing the pendulum back towards its equilibrium position. So this theta can be rewritten because this is an angle theta, and we know that an angle in radians is equal to the path length along the circle divided by the radius of the circle. So that's the same as S over L, where S is the displacement from the equilibrium along the circle, and L is the length of the pendulum string. Now we can take this expression that we just derived and simplify it further by looking at the small angle approximation. So we know that as long as the angles are small, as long as we don't pull the pendulum too far away from its equilibrium point, but we keep it within, probably 10 or 20 degrees or so or less, so maybe around 10 to 15 degrees or less, then if we have just a small angle, for small angles the sine of theta is approximately equal to theta, where theta is in radians. So if we replace the sine of S over L with just S over L, we get this expression for the restoring force, for the force that's bringing the pendulum back to its equilibrium point. And if we make an analogy with Hooke's law, we can see that it looks kind of similar. We have a minus sign indicating we have a restoring force bringing it back to equilibrium. We have a displacement from equilibrium, and then we have some number out front, which depends upon the physical characteristics of the system. So we can make this analogy that S is like the displacement in Hooke's law, and mg over L is just like the spring constant. So if we use those similarities, we can then write down expressions for the frequency and the period. So a pendulum, we can say, as long as the angles aren't too big, acts like a simple harmonic oscillator with a spring constant equal to mg over L, where m is the mass of the weight on the end of the string and L is the length of the string. So we can write down the angular frequency, 2 pi f, which is equal to k over m for a simple harmonic oscillator, for the mass on the end of a spring, and then we replace k with mg over L. We see that the masses cancel, so we get that the angular frequency is equal to the square root of g over L. Then the frequency is the angular frequency divided by 2 pi, so we can get an expression for the regular frequency in hertz. And then we know that the period is 1 over the frequency, so the period has this form where it's equal to 2 pi times the square root of L over G. Now this expression is actually very interesting because it tells us that the period of a pendulum doesn't depend on the amount of mass you hang on the end of the string. It only depends on the length of the pendulum. So far we've been looking at a very simple pendulum where we have just a single mass on the end of a string. There are some things that swing that are called physical pendulums because they're not perfectly modeled by a mass on the end of a small mass on the end of a string, but actually have mass all the way along. So if we think about this pendulum in this clock, this would be a physical pendulum because there's not just mass down here at the end, but there's mass all along. So for a physical pendulum, for an object that's swinging back and forth and has mass distributed throughout its length, then you have to use a different expression for the period. And the expression looks like period is equal to 2 pi times the square root of the moment of inertia of the pendulum about its pivot point divided by the mass of the pendulum times g times d, where d is the distance from the pivot point to that object's center of mass, or where it would balance. So we should do a check on this equation and see that it agrees for what we already know about the simple pendulum. So for a simple pendulum where you have just a very small mass on the end of a string, we know that for this simple pendulum that the moment of inertia is equal to ml squared because you have a single mass going in a circular motion. So a single mass going in a circle always has a moment of inertia equal to mr squared, where r is the radius of the circle, and in this case the radius of the circle is equal to the length of the string. Then also d, the distance from the pivot to the center of mass, well, all of the mass is here. So the distance between the pivot and the center of mass d is also equal to L. So we can put in what we know for the moment of inertia and that d is equal to L. We get some cancellations and end up with that the period is equal to 2 pi times the square root of L over G, which is the expression we had before. So this check shows that this is a general equation that works for all types of pendulums, and in the case of a simple pendulum, it reduces to the formula that we had derived before.